Now we're going to talk about dilations. Dilations, another way to look at that is something called a size change, and you'll see from the notation that it's actually going to connote that. Okay, so a dilation is a change in size of a shape. Now, does it preserve orientation? So simply put, if I were to do a dilation, which is pretty easy here, A, B, C, right? And if I select that, and I copy and I paste it, and all I do is I grab it, and I make it larger. Yeah, I think it's pretty straightforward. If you look at the orientation, this orientation could be ABC, right? Which means this orientation is indeed ABC. So indeed, yes, it preserves orientation. Is it isometric? I think you'd agree that these are not the same size. So this is actually our first non-rigid, right? Non-rigid. So it's not a rigid transformation. It isn't considered non-rigid. Go figure. And that means it's not isometric. Now, center of dilation. So we're going to look at exactly the effects of a center of dilation. For our purposes, the center of the dilation is going to be the same as the center of, or center of dilation is going to be the same as the center of rotation, which is the origin. We're going to play around with how that relates to the scale factor, which is the next thing, which is how much we're changing this. So if we were to look at this, let's say that this was 5 units long, then if we were to dilate it by what is called a scale factor of 2, it would become 10 units long. Now, scale factor is a one-way thing, meaning if I take 5 and I multiply it by 2, I get 10. But if I go the other way, then I don't multiply by 2. In fact, I divide by 2, aka, because it's always going to be multiplication, we're going to talk about a scale factor in the other direction of 1/2, or the reciprocal, right, of the original scale factor, or at least the scale factor in the other direction. So scale factor is how much, because it says factor, we're multiplying length by. It's important that it's length by in a dilation. Okay? So literally scale factor 2 means we're doubling it. Scale factor 3, tripling it. Is it possible to have scale factors that are fractional, like 1/2? Of course it is. Is it possible to have negative dilations? Yes, and we'll talk about what that does. Now, dilation notation, I told you this is where dilation often messes people up. We think of these as size transformations. It's going to be S of K, where K is the scale factor. So S of 3 would mean the scale factor is 3. What we're multiplying by is 3. So let's take a look at some examples. Not there. Not there, but here. Okay. So what we're going to do is go ahead and do a dilation centered at the origin, and we're going to apply this to an object. Now I'm going to do scale factor 2. So if we take a look at AB, its length is 2. And so if I apply that, there's A prime, B prime. Let me drag this down here. Let me try to drag this down here. Let me go here. No, I can't drag it. Construct. No, I can't. Oh, sorry. But what I have done, now let me do this then. I can actually move this. So there. Good. Okay, so this actually will illustrate a couple different things. So I've done a scale factor 2 dilation, and here's the deal. If I were to draw a line that connected the origin and this point, and then extended it through this point, right, that would be the line on which I stretched or dilated that point. And if I do the same thing with this vertex, I get the same effect, okay? And likewise, it's not a coincidence, there's actually a reason I'm pointing this out, is if I do the same thing from here through B, then it maps straight on to B prime. So we can start labeling some stuff here. We know that this is B prime, this is A prime, and this is C prime. Now, how are the coordinates affected? Well, if we take a look at C, it is at 3, 0. Now, if we take a look here, C prime is at 6, 0. Now, if we do a scale factor 2, or size transformation scale factor 2, right, scale factor 2 dilation on the point 3, 0, obviously it becomes 6, 0, meaning we take and we multiply everything by 2, okay? So B, which is at 4, 2, becomes, well, what's 4 times 2? 8. 2 times 2 is 4, right? That's what B prime would be. And so then if we take a look with A, which is at 2, 2, then we see that A is going to be at, A prime, sorry, is going to be at 4, 4. And if we take a look at the distances, AB, the length of AB is equal to 2. What is the distance between A prime and B prime? 1, 2, 3, 4. So we know that A prime, B prime is equal to 4 also. Now, this is where the fun really begins. If I take a look carefully at what's going on in terms of, let's go here, the distance from the origin, O to A, right? That would appear to be going up 2 and over 2. Up 2 and over 2. Now, if I take a look at the distance from O to A prime, what have I done? I've gone up 4 and over 4. So if I take a look, and this is going to require that you think carefully. Oh, you know what? Let's look at something a little bit easier. But would you agree that if I'm going up 2, and over 2, that twice that would be up 4 and over 4? That is, if you think about the hypotenuse, this is going to be 2 squared plus 2 squared, and then take the square root. This will be 4 squared plus 4 squared, and take the square root. Or another way to look at it, if I take a look at OC, its length is simply 3. That is, from the center of the dilation to the pre-image, and then the center of the dilation to the image is 6, which means that it's multiplied by 2, aka the K, the scale factor, right? Now, we talked about negative. Let's take a look at negative and see what that does. Let's do this and slap a negative sign on here. And what happens? Well, let's take a look. Let's try this. Let's grab you. Actually, we'll have to redraw our lines. So let's get rid of all this stuff. And let's draw a line that connects the origin and A, and then extend it. Except this time, instead of extending it from the origin through, in what is the positive direction, we're extending it in the negative direction, right? And if we do the same thing here for C, through the origin, this ends up being C prime. And likewise, you guessed it, with B through the origin to B prime. So then we can go ahead and label these out. B prime, A prime, and last and certainly least, well, maybe not, but whatever, C prime, yes? Now if we take a look at the distances, because this is still O, origin that is, OC is still equal to 3. What about OC prime? 1, 2, so at the start of O, turns out to be 6. They're still related by twice the distance. The only difference is the negative direction causes it to go in the opposite direction of the original shape. So this direction is positive in terms of dilations, and this direction would be negative. Let's make that look actually like a negative, right? A negative in that particular direction. Likewise, positive towards B, which means we started the origin going negative, right? Are the lengths still the same? Well, AB is still 2. What about A prime, B prime? 1, 2, 3, 4. It is still 4. So everything else stays the same. So that's my introduction to dilations.